Hello, academic stars. Welcome back to Caltex Academy. Today on our board, we're looking at this examination question picked from Earth Geometry. And in this question, it says, in the diagram below, A is having this coordinate of 65 degrees north and 5 degrees east, and that is our A. B is 65 degrees north and 45 degrees west, and that is the location of B. And C is not mentioned its coordinates. 3 points on the surface of the model of the Earth, and O is the center of the model. So this is O as the center of this model. The point C due south of A is such that AOC is 82 degrees. So point C is due south of point A, and we have the center here. The angle given for us as AOC is 82 degrees as mentioned here. And somewhere we shall be using pi as 3.142, and the radius of the Earth hour as 3,437 nautical miles. So let's look at how the question is demanding us to do. Now the first question is saying state the longitude of A. State the longitude of A. This is the longitude of A. How do we know this longitude? Just simply come and trace from the diagram here, and you see that it is 5 degrees. Now this one does not require us to do some calculation. We simply come here and say this is 5 degrees in the eastern hemisphere, and that one is done. That's correct. Now next, we go to part 2 of this question A. Calculate the latitude of C. What is the latitude of C? Now, for us to get this latitude of C, what we have to do is we need to make some small arrangement here. So I've just brought us down to a certain diagram here. If this is a center of the latitude down here, and we know if we join this center, maybe let's call it as center D, this center D to point C, and again we have another point here as the center, we can call it as E. Then we can also join this to this center E. So let the latitude be alpha. Now alpha is what we don't know, and then beta be the latitude at A, and that is 65 degrees. So for us to be able to get this alpha, we'll take a look at here. This line and this line are parallel. And if they're parallel, the same angle here is 65. So if this is 65, of course we know that the latitude 0 degrees around there. Now when you join this point up to here, this line is parallel to the two lines here. Now this angle is the same as that because you can see is the properties of Z angle. So this is 65 degrees. Now since we have let our angle at C to be alpha, meaning from here we also have what? Alpha. And again this one is Z angle property. You can have this one as what? Alpha. Now you can see from here that the sum of these two, because they're from different hemispheres, will give us this angle here. So simply we can add the two angles together given by what we have just notated here, and we have alpha. If we add alpha and beta together, you must be able to get that angle difference 82. So we can go ahead and substitute for our beta here because we know it as 65 degrees, and this must be equivalent to 82 degrees. So let's collect like terms, and we have alpha is given by 82 degrees minus 65 degrees. If I enter this into a calculator, I will be able to get 17 degrees. So alpha is just 17 degrees in the southern hemisphere. Now we can happily bring it down here and say this is 17 degrees in the southern hemisphere. And that answers this question, which is asking us to calculate the latitude at sea. Now let's move to part B of the question and say, calculate in nautical miles the shortest distance. Number 1, between A and C. So the shortest distance is this part. I think since we already understood what we have here, I'm going to erase this notation I've just given here for us to have something clean again. So here let's maintain maybe our 17 degrees sort of this line down here. And remember, the shortest distance is from A and C. So it's not this curved, but it's something that moves straight from here directly to C. Now that is the shortest distance. And we know this is the radius of the Earth, and this is the radius of the Earth. What happens if we extract this out? Now, assuming we have this extraction and we make some triangle kind of thing where our A is at this point, so C is at this vectors, and naturally it is curved here, but since the question is requesting us to get shortest distance, then we may look at AC through the straight line, and this is the radius of the Earth, R, from the diagram here. Now the center degrees here is 182 degrees. Now first to get the shortest distance, we need to drop a line from here to meet this point, and this perpendicular line divide AC into two equal parts. So if we call this one to be X, and also call this one here to be X, of course this X distance from, maybe you can call this one here as M, as the midpoint. So AM is equals to MC, now is equals to X. So it also divide this angle into two equal parts. Now 82 divided by 2 will give us this as 41 degrees. And we know our radius. So for us to get this X, we can use trigonometry, and it's saying sine of this angle, let's call it maybe general theta, maybe divided by 2. Then we can make the substitution later. Sine of theta over 2, and as I mentioned earlier on, this theta is the 82 degrees here, is given by opposite, and our opposite here is X over hypotenuse. Hypotenuse is OC, and that is R. Now our main aim is to get X, so we can multiply both sides of this expression by R. Now let's write this again, and we have theta divided by 2 is equivalent to our X over R. Now multiplying both sides here by R, we'll have here also by R, and this R cancels, so we're only left with X is equivalent to R sine of theta over 2. Now this is from M to C, and then also from A to C are identical, they are the same. So therefore AC in the shortest distance there is given by X plus X, and we know X plus X will give us 2X. Also our X is what we have just gotten here, so our AC is given by twice R times sine of theta over 2. So this is a small formula we may use to calculate the shortest distance from A up to C. Now from here, we can go on and make our substitution here, bringing our formula up that, okay, our AC, the shortest distance is given by twice R sine of theta over 2. And we already let our theta to be equivalent to 82 degrees. So making substitution to get our shortest distance, we have 2 times the value for r in nautical mile, 3437 times sine of 82 over 2. You can even go ahead and write this exactly here. Now we have our AC is the same as, let us have this multiplied. So we have 2 times 3437 times sine of 41, and this brings for us 4,509.765. Now we can round this one here to 3 significant figures, and we have AC is approximately 2,4,510 nautical miles. Many students misfire this kind of question. If they're given, they rush without understanding and just calculate instead the value of that distance AC as this curve here without considering what we have just written here. At the end of the day, you find something wrong. So just let us try the error somebody can make. Remember, AC as a curve is different from here. They have different answers. Like if you need to get AC as a curve, sorry, let's use a different color here. We will have it as the angle at the center, theta, over 180 pi and r. So this is different from what we had here. If you calculate, our answer will be slightly higher than what we have here. For the purpose of comparing, let us take a look. Our theta is 82 over 180 times 3.142 times r, and that is 3437. Let's enter this into a calculator and see what results we get. So you can see here that we can get an answer of 4,919.56 and so on. So when you don't read it with understanding, you'll see the difference here. We have 4,900. Meanwhile, we have here 4,500. So this one is the shortest distance, not the curve, not this one here. So you have to remember this formula in order for you to get it correctly. And this only also works for if it is in the grid cycle linked to the center. For a distance not linked to the center of the Earth, then the calculation is somehow different from what we have just given here. So with all this, let's move to the next question. So also the next question is asking us to get also the same shortest distance in nautical miles between A and B. Our A is here, then B is somewhere here. So what is the shortest distance? And exactly this one brings us back to what I've just explained here. Now let's start with analysis here. We are going to take some point at the center here. Maybe let's call this one here to be the center of this small circle at the latitude of 65 degrees north. Now, when we join this point B to our center, now we can call maybe this one as D as the center. We also join A to the center D. Then we have that angle difference. We use theta somewhere. Let us use phi here. And this is a small radius r because it is a small circle also here, not a great circle. For great circle, we have capital R. Now with that, how do you get the shortest distance? Remember, the shortest distance is also something that moves from here by that. It's not this curve. Now for this diagram to look a little bit clear, we can extract it out somewhere here, and we look at it as something that looks like that, something that looks like here. Now our shortest distance, let's give it a notation of B and A with our center D, then phi here. So for us to get phi is the angle difference, we have to look at these given longitudes, 45 degrees west and 5 degrees east. So they're in different hemisphere. Then we can add them together. So phi is given by 45 degrees plus 5 degrees. And this sums to 50 degrees. So that is the angle difference here. Now, what is important also here for us to get a formula similar to what we used earlier on down there, we can join point A to B, and after joining these two, we will also have to drop a perpendicular bisector from D to meet AB at a certain point, maybe say M. Now, this again, divide this into two equal parts. If we call this X and this X, remember our small radius R is given by capital R times cosine of this angle, and the angle A earlier on we call it to be alpha, so we can call this alpha here. Now if you do the same thing like what we had somewhere there, then the distance AB would be calculated from twice R and this cosine of alpha times the sine of this angle phi divided by 2. This is the phi divided by 2 because we're talking about this part only, and that is phi by 2. So let's use this to calculate the answer for our last question here in the space down here. Therefore, the last part B, Roman number 2, is AB as the shortest distance is calculated from twice R cosine of angle alpha times sine of phi divided by 2. Now we can make substitution. Our AB is equivalent to twice the value for R is 3,437 nautical miles times cosine of alpha, and alpha was 17 degrees. So we say 17. So we have 17 degrees times sine. And here we have phi as 50 degrees, but remember it's divided by 2. Now we can enter this into a calculator to get our answer. So this becomes the shortest distance between A and B from that small circle up here, and that is the small circle in the northern hemisphere. If you enjoyed this video, please give it a thumbs up, subscribe to the channel, and share the video with friends. See you in the next video. Peace out.